topic called Analytical Animation with New Views on Physics. And hopefully we're going to come to an understanding of this new graphic representation of information. And maybe I should just spend a while right on the starting slide so we can really understand it. The animation itself is front and center top sort of thing, and this is literally adding one quaternion to another quaternion over and over and over again. Okay, so this is probably a collection of, I don't know, maybe 600 quaternions. But what I found was that if I got into more complicated situations, I didn't understand the animations I got out of it. It's like, I really think our brain will have trouble doing things with animation, being analytical about animation. What I found it easier to do was deal with the pretty complex planes, so I have this time versus y, time versus how much up and down. I've got time versus z, it's going into the board, and time versus x, which is whether it's left or it's right. And then what I did was I took every single one of those images and I merged them all together to make that thing that's in the upper or right corner. That's the superposition of all possible states. And I hope that sounds vaguely like quantum mechanics. I'm hoping it actually is quantum mechanics. When they say the wave function, I point to that. And then they say, well, if you actually go and look, out of all these possibilities, you're going to get one of those things that blink right at. So it's possible that we've got a real technical picture of the wave function, and we've got a picture of the collapse of the wave function a bunch of times. And further, though, and this was one of the things that I got out of doing all this prep work. I realized that that's really more classical quantum mechanics, as it's called, not relativistic quantum mechanics, because if it was relativistic quantum mechanics, I'd have to be coming in from like 16 different directions, and I'll get to that later, but that was one of the results I got out of preparing for that. Okay, so... oh, there it is. Okay. Exactly. It's determining this. Okay, so I mean, we'll get a much better feel for this when we see the software at work. So let's talk about René Descartes. He's a classic French guy or what. His contribution is one of the longest lasting out there. Analytical geometry. Take this equation, here's the picture. I love those pictures. I can see stuff going on. It feels so real and concrete. And so then Newton comes along, actually Newton before. Newton said that time is completely separate from space. And he said that because his math forced him to say it. Now, that is happening. And it was Einstein who said that time can mix with space. He's got his life flown separating the past and the future. But it was Minkowski who actually said, no, in a math sense, it really is this one located reality. Sure. You haven't seen that before? Okay, well that's an important picture to appreciate. If changes in time are exactly equal to the changes in space, then we're traveling at the speed of light. Now, in this room, we're not. Well, what does that mean? It means the amount of changes in time are far, far larger than our changes in space. We just sit around and we're talking and talking. And I actually have a piece of artwork to go to do this very separate. Where if I'm talking, moving very fast, we get a few chances to talk to each other, and then that chance is gone. So there's this continuum of hanging out, changes in time to huge compared to changes in space. And then making this progression to the point where we get the light that changes in time are exactly equal to changes in space. Well, when you're talking about how fast are we moving, we always have to say relative to. Okay? You and I sit in this room, yeah, we've got a little bit of movement relative to, but virtually nothing. Okay? So we just sit around and watch our clocks to the left. That's the point I want to make. Oh, yeah. No, and as a matter of fact, you are moving relativistic to cosmic radiation. You're at 0.99% to what you do on. So you're moving relatively. It's kind of a funny idea. Well, I haven't quite gotten so that 45 degrees is the way we're trying changes in time to get changes in space. And what's cool about that is that anything inside the light cone, it means that you could get to it repeatedly and put it in that energy and work. But if something is outside the light cone, you can't get there. Okay? That doesn't mean it won't influence you at some later time. You know, they might throw a spitball at you, and it might hit you eventually. Okay? And as a matter of fact, I think that basically classical physics is all the physics that is actually within the width of this line. In fact, it's probably a millionfold smaller than the width of that line. That's where all the classical physics actually happens. And it is my kind of speculative interpretation that classical quantum mechanics happens kind of in the width of the space-time. Okay? In other words, those things that we can never reach, they still are there, and they're still going to kind of affect us. And what can we say about them? Well, we're actually pretty limited in what we can say, but we can say very precise things. And I think quantum mechanics is the study of the precise things we can say about events that happen along that sort of line. And then relative to quantum field theory is in the rest of that space. So I hope that gave you a little bit of a sense of what. All right. So I'm thinking about Quaternion as events in space-time and four numbers that you can add, subtract, multiply, divide, and do all kinds of things. And let me actually just demo the software for just a bit here. So I'll bring up. So this is all software that I've written, and one thing about the software I wrote is that I'm a big fan of the command line interface. Are you familiar with that? No? No, that's okay. Yeah. Here you are. Okay, good. All right. So command line is things that you just type. You just type a few letters, and it'll spit back stuff. And the reason I'm a big fan of this is because computer technology, you may have noticed, changes rather quickly. And if you say what has lasted like 30 years, it's basically almost nothing, except the command line interface. And why is that? It's because you deal with small commands. And those small commands are, they're small, so they're robust. It's not like I've got this huge, stack of software. And secondly, I can type the results of one command. One command does one thing, and I can, let's call it type, into another command that does something else. And so what you do when you do that is you can come up with permutations. And so you get kind of the power of permutation with small commands. Now one command does this one, one command does that one, and I can pick the result of one, type it into another, type it into the third, type it into the fourth, okay? And how many possibilities can you do? They're pretty linear. So, and I didn't like the idea of investing, say, in Java and then finding out that Java was changing and changing and changing. I wanted to build a tool that I could come back in 5 years and 10 years, and it would still work like it did when I wrote it. So
you just each one of those instructions is a command.
Command. Let me show you an example. I preface these commands with Q1 just prints a 1, a 0, a 0, and a 0. Okay, that's not a difficult command. I've got a Q0, which will do the same. But if I do LSQ, yes. See, so these are all these Quaternion commands, taking arc sine, exponential, Q random, et cetera, et cetera, et cetera. So, but actually, yes. But yeah, they're all C programs. They're all C programs is actually what I should say. So if I go Q add 1, 2, 3, 4, 5, 6, 7, 8, it comes back and says, oh, that's 6, 8, 10, 12. And if I go and I can basically then take that result and pipe it into the Q sine function, and I get some numbers back, and I go, I have no idea what that means. Okay. But one of the more important ones is called, constant linear motion. Let me just see what it reads in one integer and 8 real numbers, and it just kind of makes a whole series of them. So let's do 4, 1, 2, 3, 4, 1, 1, 1, 1. Let's see. No, that's not. Oh, okay, yeah. So it started at 1, 2, 3, 4. It took 4 steps, and it ended up at 1, 1, 1, 1. Okay. So if I think that work is 4,000, or the 4,000 steps between those two numbers, I can now take those 4,000 between, type that into the Q sine function and go, boy, am I really confused. What the Q says. But the point is that I can make a whole pile of different. Okay? You say, why would you do that? Because, actually, let me just change this command just a little bit to, let's make this to 10. So this is going forward, and this is going from a time of 1 to 10. You see, this is nicely ordered. But what if I now take this and pump it into one of those Q sine functions? And you go, oh, this is bouncing all over the place. And, well, what I do with my animation software is I say, I'm going to sort these based on this first number. And then there's the minus number, the smallest, so the biggest minus number, up to the biggest positive number. And then I am going to say, put this in a 10-second film. Okay? And based on this number, that will decide which of the frames in the film it will notice. And then once I'm there, I'll use these two numbers, the X, the Y, and the Z, to decide where my little yellow dot is. So if you do that, then it means you can use a program like Q polynomial, I believe I got here. Q poly. Let's see what it says. Okay, so it basically you can get to you can start to now create a polynomial, a Quaternion polynomial, and have it generate a bunch of Quaternions, and then make an animation out of that. And once you can animate the polynomials, you can animate anything. So actually, let's see if that command works. Whether my help notes were okay. So it's, I think we're saying any. Let's see. Copy. Nope. I didn't copy and paste right. So let's just skip that. but at least conceptually, I should say I consider this this bit of software I've written somewhat user hostile. Okay, it's not a really slick interface, but at least for me, it's been pretty powerful. So that's kind of an introductory sense of the software. All right, so this one we should know about. Quaternion addition is an inertial observer. So this is the simplest kind of operation you can do, and yet it's very unique because it's connected to such a relatively very directly. So, oh yeah, this to me is really fun stuff to think about, because we think we understand real numbers and complex numbers. I mean, the way it gets taught is that simply we've got the real axis, over here, and we've got the imaginary axis over here, and there's just this 90-degree rotation. That's been taught for an awfully long time. And there's something unsatisfactory about that because we know this has different properties than that. And yet there's no reason why they have different properties. Yes, they have different properties. I accept that. I know it's a very productive thing to do. It's just, I wish I had a picture of it. I think that now we will. All right. So all I'm doing with this animation is I'm going from the corner pocket up to 0, 0, 0. That's all I do in this one. So this is the same sort of common thing, but I'm really when I come to, so there's my time, and we're pointing it up to the 0 time, and then this is it. Okay? This is the setup. Okay, so now what is this? What I am doing is doing a reflection in space. Formally, I'm taking the conjugate, and what you can see happening here is that I have this mirror reflection going on. So it's like something, I got a mirror, and I can see that when I get to 0, it goes away. All right, so, and visually, when I do this conjugate operation on my conjugate in blue, the conjugate is in blue, I always see 2 strings on the top, 2 dots on the string, which makes sense. It's a mirror reflection. All right, so now I am doing a time reflection. So instead of having time be positive, I'm having time be negative. And so when I do that, it looks different. It comes up to 0, and then it goes and takes a step back. So that visually is different. I mean, it's the real number that's getting responsible. When I put an imaginary number, it's mirrored, and I can see that. When it's the real number being put, I see it going forward in time and reverse. So events go in exactly as they come out. So now I'm doing all 4. Okay, so it appears like there's this continuation going on. So I've got in yellow, that's my input. Okay, the green one, the blue one is a reflection in space. And then I can do a reflection just in time, or can do a reflection in time and in space. So the continuity of this is kind of thing you can share after a while. Like you said, so it does take a while. Okay, so if we think about the yellow line going into, say, the red line, the yellow sitting on the red, who we see? These are the ones who reflect, does both mirror reflection and the time reflection. Okay? And so, let's see, the one that's in blue, that is the space reflection, and he goes on to the one that's a time reflection. So it's fun to see the connections between these little things. And all we've done so far, I've seen this, and given a few times. It's tricky. It's tricky. You can see why I enjoy this. Like, how do you make this figure 8? Well, I took a circle in, I took a sine of sine with a future, 3 over 2, sorry, 3 over 2 in sine, and it's like, wow. And, you know, from a sense, it's doing the circle in 2 pi for this guy, 2 pi for that guy, and it's got to work hard because of that factor too. It's got to go 4 pi in order to do this sort of thing. And my critique is that, you know, there's really no need for supersymmetry. So supersymmetry is this tool where it says, oh, I've got to get, you know, something that has spin 1 and spin 1/2, and how could I possibly have a particle do both of them? These animations like this say it's not a problem. You know, I'll put whatever kind of symmetry I want to in one of the x's or the y or the z. I can combine them.
So this is a reality more information than that people think it is physical.
I think the point I'm trying to make is that you can do, because people like to think of things as being in separate boxes, you know, and that when you really think about time and space together, they really can do more in your little room together. I mean, I didn't expect to get a figure 8. You know, I just said, I know how to generate this. I have no idea what it's going to look like. I certainly was surprised that it came out of the figure 8. I was certainly surprised that it certainly looks like a hyperbole. Okay? But it's actually a finite hyperbole, which is another thing I hadn't had experience with. You know, when I draw a hyperbole, they have to extend out to infinity. But, you know, a circle doesn't extend out to the infinity. And by the way, every moment here is reflected in there and is reflected in there. You know,
what I was getting at is
yeah.
matter is, in a sense, spatially confined energy. When you really get down to it, it's nothing more than the distortion of space-time that you're seeing and it's all about. So what we consider reality, meaning mass, energy, you know, all this, is nothing more than math. I mean, when you're dealing with a mathematical representation, it may be what it is.
I had somebody say to me once, I thought it was space-time. That's like vague enough to be true. Okay? And that's how I feel about it. And I don't mean to be insulting. I hope it's not. It definitely is along that line. This graph is just trying to say, you know, it's almost like what happens with clouding. You know, how in the Olympics, you know, they're spinning this many axes along this axis, and they're spinning that way on that axis, and you know, they're going on the third axis of this thing. I think there's a lot more possibility. That I just don't see the need to keep the strings because I think I have to really separate all this. Really quite simple. It's not that.
So what is this display you have to replace supersymmetry with?
I think I haven't done that, in a sense. In other words, supersymmetry really is the formal body of physics work. Okay?
You are the only participant in this conference. Press any key to continue this conference.
Yeah, because I did.
Press any key to continue this conference.
Particle physicists are profoundly stuck.
Press any key to continue this conference.
That's the wrong thing. There's no presenter. Sorry about that. So what is supersymmetry?
So the particle physicists are really stuck. They can't figure out how to get gravity in with the rest of it. And we take my point of view with it. Okay? Because I think the future maybe it isn't that. I could say I'm only using the Quaternion math called tensor math. Okay, thanks to the same darn thing. That's the way I got the math right. Exactly. I mean, I got to be straight on two straight. Not exactly. Okay? They are profoundly stuck because there's no way to get from that to a theory of gravity. You can get to a theory that works really, really good. That's general physics. It works really good. Okay. But we're drawn to, as you told me, this is a little bit I digest, but I hope you like this digest. So we're drawn in for general relativity. There's mu naught, because I can write it down here, and I bet you can remember it. It's one letter long, okay? That letter is really hard. I don't completely understand it because it's the contraction and the contraction of the rhyming curvature tensor, which is like way up there in the sky as far as figuring out and understanding. But if you go, why can't general relativity get along with the standard model? We go, this guy is in his room by himself. He doesn't care about anybody else. There's nothing else here. You'll also hear very often, oh, general relativity is really elegant. It's amazing. Well, it is. But there was Brown's level. But this one isn't going to play with everybody else. Okay? So, the particle physicists working with only effectively Quaternion can't get to the theory of gravity because they're not going to go use hyper-complex numbers, which are even less popular than in Quaternion. So, so given that box that I think there is, okay, they're saying, okay, what can we conceivably do? And you have a lot of basically the brightest people on the planet, and what can we possibly do? For years. And they came up with an idea, and that idea was supersymmetry, where every particle that we know, and we know is about 400, has now a partner, a superpartner, okay? And that superpartner, well, we haven't seen one yet, but it will allow us to do and think all kinds of new ideas. And that's hard to think about. I mean, I can't follow when they talk about it, okay? But it's a serious technical effort to get the standard model to do stuff that is worth the craft. And I think that's probably not a physics question. I just know they have to double all the particles out there. I know that they're looking really hard for it. And that's another one of the things that we're trying to do in the Large Hadron Project. Okay, we've got $10 billion on the line, and we really want to see we really want to see a superpartner, and then we will suppose that there are lots of others. But until the time is big, and until the time is superpartner, it's anybody's guess what's going on. And it's probably secondary.
sound more like a colonnade century or so, where everyone thinks something that's not really right and broken, and then the whole puts a little package to it, and then we incredibly complex, when in fact we just had it wrong.
That's almost like I think that you got to end up that, right? There's a lot of sincere genuine effort with strength. And I haven't insulted those people, okay? They are hard workers. They are in a similar kind of bind. They, in fact, work off of supersymmetry, and they do other things beyond that. And to me, when you start animating, just one, two, or four numbers and really put them in a pile and start looking at it, these don't look like things I'm used to. And I'm kind of taken aback by it. Really. So I don't think we have explored good old three-dimensional. I shouldn't say four dimensions. This is another one of my little tweaky things. Because if I say four dimensions, it sounds like it's three dimensions plus another dimension. Okay? That's a little misleading. And it's important you get the fundamentals right. Because three dimensions, those are pointy. Those have the arrowness to them. That's four? No. The three dimensions of space and a scalar, time. There's no pointiness to my plot. Okay? That's what I'm dealing with. It's not four dimensions, a scalar and a three vector. And if you keep that in mind, then you don't get into a fault. Why don't I go up to 7? Why don't I go up to 10? Okay? Because well, how did the scalar go? Oh, the scalar didn't go. It was all n. So that's my own little thing. So,
But also every time you go up, you just stop, you will eventually start from all ease of basic words of algebra.
here is that true. Here is that true. But what I was saying, I had the most wonderful time in my own head dealing with three dimensions of space and time. And so let me give you just another super concrete example. Here's this group called SU2. It is a group that is involved with the weak force. Okay? And if you say to someone who's really professional out there in group theory, what does that look like? They're like, what do you mean, what does it look like? It doesn't have a look. And you go, but it's only using three numbers. Shouldn't you get some picture? Can't you get something out of it? And what they can write down is they can write down a Quaternion exponential function, where you take the Quaternion and you minus its conjugate. That's basically a way to knock out the scalar. You knock out the scalar, you have three numbers, and you just take the exponential of that, and that will always have a normal 1. Because it's like e to, if you say, what's its norm, it's like e to the I, and e to the minus I makes up e to the 0, or that equals 1. Okay? So math-wise, this is rock solid. And that's as far as they go. I shouldn't say that's as far as they go. There's very sophisticated, there's interconnections between these various things. But they won't say, let me make a okay? And I said, I want to make that. And so what I did was I just put random Quaternions. That's what this represents, actually. I took literally, 10,000 randomly generated Quaternions. Using 2 random 1,000. Okay. Then I typed it in this function called Q vector, so I would throw away the scalar. Then I would type that into Q exponential, and then I got this pile of numbers. And to me, it's profoundly wonderful, ironic that you see this pile of numbers go by and you say, I have no idea what this looks like. And then I've got another piece of software that says, okay, thank you for generating that. I will make you the sum. And this is what we get out of it. And it took me a while to understand. But it's good to start with these shadows. You see the shadow in the animation? Okay, it's basically starting in about 8 different points. Okay? And the points are going to grow into each other and connect and make circles, and there's a sphere that goes and does. This is another profound philosophical aspect of this, is that everything is finite. And so So I just keep on cycling it so I can start to get it. Okay, so what happens is you start to say, this final point I understand. That is, that's when the space part is shrunk to nothing, and all I have is a time component. And that time component, where is it in space? Because it's basically looking 0, 0, 0. So all this activity is like, and where it reaches its maximum distance right there. You know? Okay, that's a very valid question. So I've got the value of t, the value of x, the value of y, and the value of z. And those are the numbers. Alright? So what I do is 3 pairwise graphs. T, actually, let me use my thumb for this time, because that's easy. Time and x. That time and x goes in this particular. Time and y goes in the other one. Time and z goes down here. And when you glue them all together, now, no, this is something I don't have the ability to really do. I don't have the ability to go, oh, because I see what's going on in these three, I know it's going to be go on in the animation. I don't have that ability.
Is there really an emergent nature in this field? Do you really think about that process?
It's one of those things, maybe you become an expert at this, eventually you'd be able to, yes. So I look for much simpler things. I can hold on to the simple things. It's like, I start out with nothing. Something's coming up. Okay, there's some kind of turning point now, and everything's going to click. Those are the three things I get going from the complex from what goes on in the animation.
It's highly determined. So what word do you use to describe it? Do you have a highly deterministic? Is it somewhat chaotic nature?
It's not
a fairly emergent nature?
I think it feels emergent like that.
Emergent.
Yeah. What data here? Yeah. Because of the way that this is generated, I used 10,000. If I would have used 100,000, it would have gotten to these numbers. Yeah.
So there was much different if they used 1,000.
Yeah, well, it looks more vague.
Was there a point
Oh, yeah.
20,000 be any different from this, or was 5,000 be any different from this?
I would say that there's a transition from, this is really kind of rough, to that smooth.
And what would that number be roughly?
It depends on the rock. It really depends. And it probably also depends on how big a ball I throw into my 3D program. Because, conceptually, these are all events. But how big should I make my event? If I make it super small, I'm going to need a lot more points in order to see it. So part of that definition is to do the size of the series that I have to choose.
Do you have a program you can play in 3D like on the new
Not yet. I really watch that technology because it's like, I got my 3D things and I want to see them. But I haven't made that move yet. Okay, so, this is SE3, which is on your t-shirt, right? This is the star of that one. And what I love about this one is this looks like a uniform, tennis ball at the game. It starts, it gets out to the edge, and then it comes back in. And it's also, to me, philosophically satisfying, because I'm trying to say that that the three symmetries that show up in the standard model, that would be this one, U1, that would be that one, SE2, and that would be this one, SE3. What that really means is that I'm an observer. Where am I as an observer? I'm at 0, 0, 0. 0, 0, 0, and something happens in space. Okay? And they go, well, how far away was it? So they're like, I don't know, I'll just call that 1. It'll have some x to it, it'll have some y to it, it'll have some z to it, it'll have some time to it. Maybe it was back of me in terms of time, maybe it was in the future. Okay? Whatever that was, and I don't even know what caused it, is on this unit sphere. This is an animation of the unit sphere. And yet I connect it to the symmetry that are the standard model. And it feels like I'm done. You know, I can't do kind of more than this, which is cool because that's what the limit on what, you know, the limit that appears in the standard model. It's these three groups, it's only these three groups, it's not more than these 3 groups. And I go, yeah, because we're trying to deal with the unit sphere. Something happened in nature, and somehow it gets all connected. But it starts to get a little hand-wavy, okay? And I admit that. In other words, I have no idea what's the strong forceness of this, okay? Instead, all I have is I see those groups. They're really there. And they're really forming a life object that I can understand. I can understand it's true. So, wow, there's hope there. But there's hope there, and there's also not hope there. You remember how you said, why don't you publish it? But where am I going to publish my animations? It doesn't work as a PDF, ever. Okay? It's like, that's weird idea. Okay, so this was the thing with the gamma matrices that show up in really consistent quantum field theory. And believe me, those are scary. But if you go on like this, you see. And the idea is you start with one path, and in my software, I put it on both sides by the 1 and 1 I, and I take the same selection from the other thing, and start with an I, with a 1 I, all 16 possibilities, and lo and behold, you end up with this. And so that is why quantum field theory, in my opinion, is going to be so hard to exactly the heart of it today, and will remain as long as people study it. Because it's hard to think about all the possibilities out there. And yet, apparently that's the math machine is about. The math machine is really shows and gets a lot of different ways you should take those two y and z values and mix them up. It bothers me that this is knows how to mix things up like that. That's interesting. Oh, sorry. This is good thing? But not in exactly the same four corners? Yeah, okay. That was a design decision, you see how this doesn't quite go to the center? If I went dead to the center, it would look prettier. And it would look a little less off. Where exactly that started also, I wanted to make sure the key x, y, and z values that it started with were a little bit different, and that it didn't quite go to the origin, and that's what makes it have that scattered look. In other words, if you went dead on, Q's with Y and Z through the origin, I think you would get to end up with a Oh, that's good.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil.